Howdy ho and welcome to my lecture where I will try my best to explain to you all about thin film structures, how they behave and how they can be understood as a amplitude splitting interferometers. So we will look, of course, into thin film structures because they are of practical interest, and also for many of the engineers in us, we see their great use to actually make optical components and then improve the performance of existing optical components so that they're actually highly relevant. So this is actually good stuff also, although no Fourier transforms will be involved in this lecture. But we will go basically through the math that is related with thin films, and we will form equations for the phase differences. And based on that, of course, we will derive conditions. When do we have constructive interference or when do we have destructive interference when we have the structures? And at the end, I will try my best to provide you some practical examples of different situations when we are actually seeing thin films in action, giving rise to, for example, coloration of structures. So, for example, a kind of strange-looking coloration taking place in pieces of glasses, for example. So this is what I will be saying and trying my best to explain during this lecture. So, amplitude-splitting interferometers, and now I will try my best to explain what are these other type of a interferometer class known as a amplitude-splitting interferometer. And it sounds awfully obscure, but basically what happens is that we have an incident wave, and we think that this wave is being split into two, and this is in fact what happens in these types of interferometers or more components. And then we are letting these two different portions of the same wave to interfere with each other. And then essentially how we are splitting this wave into several portions is that we have partially reflecting surfaces that then part of light is being reflected and part of light is being transmitted. So essentially exactly what we considered already in our chapter 6. And these wave components, of course, they propagate and at the different optical path differences inside the instrument or inside the thin film, inside the material. And then ultimately when these waves are let to propagate into the observation point where they ultimately are being combined, it can be a detector or it can be a human eye into which things are being focused, or it can be a camera screen, and it's there where we are ultimately either seeing interference, constructive interference, or not constructive, but rather a destructive interference. And by far the simplest possible scenario to consider is a thin film, and this is a very beautiful example. It's a simple structure, and this is also highly relevant because we can find so many different kind of thin film configurations in nature. So for example, in many of the kind of tail feathers of birds, we have structural coloration arising from the fact that somehow biologically the bird feathers, they look like thin film structures. I guess everybody can imagine how soap bubbles, they look colorful, that when we were making soap bubbles, and this is essentially a thin film structure giving rise to structural coloration, so diffractive colors. Maybe some people are into fancy looking cars, and then you can have these kind of chameleon paints where people are also utilizing thin film structures and whatnot. So these kind of interference effects are present in many different things. Or you put a little bit of oil and gas on top of a water puddle, and you're actually seeing a kind of structural coloration, diffractive color formation. And many of the insects, when you look at the kind of the insects, they may have very vivid coloration, basically arising from the same thing and whatnot. So there's a huge number of examples where we are actually seeing thin films in action. So soap bubbles, oil stains. I think even on the surface of a coffee, I will be showing you a picture of this, and tail feathers of magpie and another example, other many birds. Peacock is a classical example, I would say. So many examples exist, and this is hopefully a good motivation to go through this lecture material. So let's start by considering what we are facing, and we will do the extension into another scenario in an upcoming lecture. But for now, we will assume that we have weakly reflecting thin films. So essentially what we assume that the refractive index contrast here is quite small, so that this interface, it mostly transmits light here and only a tiny portion is being reflected. So for example, like this N1 and N2 could be air, and the NT material here, like it has a refractive index of, let's say, 1.5 or something. And as long as we don't do any particular thin film magic here to increase the reflection coefficient of this interface or this interface, this is where we can still apply an assumption that we have a weakly reflecting thin films. And this is what we assume implicitly during this lecture. But please be warned that we will extend this treatment into highly reflecting thin films in the upcoming lecture. And now, when we are considering this assumption, only two rays are of importance, and they have been highlighted into the figure. So essentially, we have two rays denoted here as a 1 and 2. And instead of a lens and a screen as given in the picture, we could also just imagine that we have a human eye that detects the rays, and this indeed is often the case when we are seeing structural coloration, for example, of soap bubbles and feathers of birds and so forth. So we don't really have a lens and screen here, but rather we're just putting our eye here, and the eye is acting both as the lens and the screen detector here. And the two rays of interest are the ray 1, that we have an incident wave defined with the wave vector ki. It's hitting our first ear something interface, it's being reflected, and then it propagates all the way into the screen. And then a second portion of the incident ray is actually being transmitted. It's been refracted, goes and bounces around, and then goes as a ray 2 all the way into the screen where the two rays are being interfering, or wavelets. So here in our configuration, D is the thickness of the film, and as the name suggests, this D parameter is usually not very much. N2 is the refractive index of the film, and theta I is the incidence angle. So these are the main parameters of interest here, and now we can start calculating what is the optical path difference between the two rays. And looking at the geometry, the figure, we can see that the optical path length difference between these two rays is essentially the distance difference between the AD length minus the ABC length here. So looking at here is essentially that the path lengths from the point D from ray 1 into the screen, this is exactly the same as the ray 2 coming from the point C all the way into the screen. So where the phase difference takes place is that we have the ray 1 propagating from point A to the point D, and then we have the ray 2 propagating from A to B, reflecting here and then into the C. So this is where we have the path length difference emerging into the scenario. And we can now just proceed in calculating these things. What is the optical path length difference? So from the figure, we can easily see that the AC distance is essentially, just looking at the figure, it's 2 times D, the thickness of the thin film, times the tangent of theta T. We can just easily see this to be true from the figure. And similarly, the AD, we can easily see that this is the AC times sine of theta I. So essentially, like looking at this AD here, we can equate by just looking at this triangle here, that it's the hypotenuse AC, and then we take the sine of theta I, so that we have the AD. And similarly, the AC, what is the distance here, is that it's basically the 2 times of tangent of theta D here, so that we can just imagine that we have a triangle here, and from that we can calculate that what will be this. So basically, we are taking the thickness D here, and then when we are calculating the second length of the triangle here, second side length. So, of course, the Snell's law still applies, as usually is the case in optics, so that the Ni times sine of theta I is equal to Nt times sine of theta T, and now we can simplify things, so that the optical path lengths are now found to be that the OPL1 is N1, the refractive index in that medium, usually air, times the AD length, and this is equal to N1 times AC times sine of theta T. And now we can use the Snell's law so that we can simplify that this is actually N1 times 2D tangent of theta T times sine of theta I. Sorry, we did not use Snell's law here. So we're just using this one here. But basically, this we know that the light is propagating in here, so that's the NI, and this is what we have used here. I think we use the Snell's law later on, but let's see where do we actually use it. So this is now 2 times d times nt times tangent of theta t, and now we are using the Snell's law here. Now I can see it happening, so we have the sine of theta t. So essentially we have n1 here, sine of theta I here, so we are transforming that into nt and sine of theta t here. And now this is equal, as the definition of tangent gives, that this is 2 times n1 times d times sine squared of theta t divided by cosine of theta t. So essentially we are just breaking tangent theta t into sine of theta t divided by cosine of theta t. And now the OPL2, this is by just looking at the figure, this is 2 times nt times AB. So this is essentially now ray 2 propagating inside the medium, that is the thin film. And this we can simply write that it will be 2 times nt times d divided by cosine of theta t. And now we're interested in calculating the path difference. So what is the OPL1 minus OPL2? So that we can now just calculate this, and we can define this. Helps our math later on, that we just use a simpler simple capital lambda, and this is equal to 2 times nt times d divided by cosine of theta t, and this is now 1 minus sine square of theta t. So this is essentially, we took the two things together, the two equations, we calculate their difference, and this is what we get out. And now this can be simplified, that this is essentially just 2 times nt times d times cosine of theta t. So here we can use the trigonometric identity that the cosine squared plus sine squared equals 1. And this can be formed that this is actually now cosine squared. And now I'm dividing that with the cosine here. So that's what's left, is just the cosine in the numerator. And let's now consider a situation where both of the media of interest that are like above and below the thin film, they are same medium, so that then the refractive index profiles of n1 and n2 are equals to n. And this, we assume that it's a different n than the refractive index of the thin film, so nt. So that they essentially they have a different optical density, so that the refractive index profiles are different. Because if that would not be the case, then we wouldn't really see much of a reflection at all, and then of course we wouldn't see interference essentially at all. And now, during one reflection, a pi phase shift also takes place. So please remember the Fresnel's coefficient into the figure of 6.7. So basically, when we have this reflection here, there will be an additional phase shift. And this we must take into consideration when we are finally calculating the total phase difference between the two different rays. So that the phase difference delta between the two rays actually then turns out to be that's the k times this capital lambda, the phase difference we just calculated, plus minus pi. So that's the additional phase shift arising from the reflection. And this is basically, we can see when we look at the Fresnel coefficient when we have a interface. And this is now k is equal to 2 pi divided by the vacuum wavelength, so lambda naught times capital lambda plus minus pi. And now we can plug in what we have discovered, what is the capital lambda, and we have a formula that we have 4 times pi divided by lambda naught times nt times d times cosine of the theta t plus minus pi. So here lambda naught is the wavelength in vacuum, and now we can see that we have interference maxima when the phase difference delta, of course, is an integer of 2 pi, as always. And now this gives us a condition that the phase difference term delta must be 4 pi divided by lambda times nt times d times cosine theta t plus minus pi, and this must be equal to 2 pi m, so that we have constructive interference. And we can now shuffle our parts and terms, and then on the left-hand side we had d, the thickness of my thin film structure, times cosine of theta t, and this is equal to 2m plus 1 times lambda naught divided by 4 times the refractive index profile of the thin film nt. And now we can simplify things slightly so that we can use the wavelength of light inside the thin film structure, so that the wavelength inside that structure, we denote that is a lambda t, and this is lambda naught divided by the refractive index of the medium nt. And now the d cosine term turns into a 2 times m plus 1, and now we simply have lambda divided by 4, where we must remember that this lambda is now actually the wavelength inside that thin film structure. And now we can simplify things even further, so that the 2m term plus 1 inside the parentheses, we can write that it's the m plus half, and then we have lambda over 2 outside the parentheses. And now we solve essentially or we have already solved the only thing we must need about thin film interference, so that we have the d thickness times cosine of the theta t is m plus 1 over 2 times lambda per 2. And this is essentially the equation that tells me when do we see constructive interference in a thin film structure. So thin film interference, this is what it comes about. And of course, as we can look into the equation above, really depends on the thickness of the film d. Also, it depends on the refraction angle. So it depends on the theta t. And since we know from the Snell's law, this theta t also depends implicitly on the refractive index of the above medium, depends on the refractive index of my thin film structure, and it also depends on the incidence angle. So there's actually a lot of parameters that the thin film interference depends upon. So basically the different refractive index profiles, the different incidence angle, and the different wavelength that changes things. And of course we have different interference maxima. So depending on the order of the interference, we may have a different condition for the constructive/destructive interference. So basically the interference maxima, they occur when the capital lambda times d times cosine theta t equals to a multiple of lambda per 2. And essentially the lambda 2, or another way of putting this is that we can solve this with respect to the wavelength lambda t. So lambda t equals 2 times capital D times capital lambda times t times cosine of theta t. So now, for example, a function like the wavelength can be seen that it's as a function of theta I or theta t, or as a function of wavelength, we have a constructive or destructive interference. And this is in fact a quite important thing, so that sorry about this again. So that depending on when we are changing the incidence angle slightly, or that the wavelength of light that we are looking at changes slightly, then we either have destructive interference or constructive interference. And this is actually the physics that gives rise to structural coloration in these kind of structures. So now I'm going to show you some examples of thin film structures, and I believe that this is an example case that we have this kind of coloration here. Of course, we don't see vivid colors here because black coffee is quite black, so that the kind of color formation is not as clear as if we would have the case that we would have just water. But I wanted to just point to you that this is also what we may see every day. Certainly I'm seeing this effect every day in my life, and this is essentially thin film structures in action and an interference phenomena in action. So we all know that the coffee beans, we also have fat lipids inside the coffee beans, and when we're making coffee, then we will have this kind of like a fat forming thin films on top of the coffee, and because of that we will actually see structural coloration. If you want to see the same thing, and you're not much of a coffee drinker but rather a tea drinker, I think that those people are highly suspicious, but my wife included. But if you drink tea, then you can see the same effect, and there I admit myself that in that scenario you actually are seeing structural coloration and actually vivid color formation, so that you see the same effect, but now you have some kind of oils in some teas at least, that they give rise to the same kind of physics. At least I remember sometimes my spouse has given me or forced me to drink some tea, and I have looked into my mug, and I have seen quite nice structural core formation in the tea puddle and in the oils on the top surface of the tea. So it also happens there, not on just with coffee, but also with tea. So we have lipids arising from the coffee beans, and they essentially form a thin film structure. Strange chemistry takes place so that the thickness of the film is quite thin, and we are actually seeing strange light coloration. So this is something that takes place in a coffee drink, and the same thing takes place also in tea. So don't be fooled that it's only like a very, very narrow scenarios when we're seeing these effects. Another example, and this is actually like a made by engineers, and this is where things have been designed to be such. And essentially, you're looking at the binoculars, and the other lenses, they have been coated, and they have been coated such to have a minimizing reflections at the surfaces of the lenses. And so these are so-called anti-reflection coatings, AR coatings, and in many of the optical instruments, they are actually being used to improve the performance so that more light gets actually through and will be seen by the human eye, so that we actually are seeing a brighter image magnified using the binoculars. And there, in essentially these anti-reflection coatings, they are purposefully designed and made by using stacks of thin films. And as you can see here, like these binoculars have been optimized that at the visible white light, and when we are looking at the top view, we would be seeing as much of light going through the binoculars, and this has been optimized by just putting some AR coatings into the lenses. And correspondingly, these lenses now, when we are looking at the given view, they actually look quite red, so that this is a good indication that there's actually some thin film magic taking place in these lenses here. So this is an example where people have been used intentionally thin film structures. So essentially they have been making AR coatings used in optical instrumentation to improve the performance of these instrumentation, such as binoculars, telescopes, and whatnot. And here is another example. This is from the Wikipedia. So we have basically a slightly curved surface. So this is a backside of a lens, and the top surface of the lens, we can easily see that this is very curved. But the fringes, the coloration that we see is actually caused by the backside of the lens. So it's essentially a plano-convex lens here put on top of a surface, smooth piece of a glass. And because there's a slight curvature in the backside of the lens, and there's a smooth surface, essentially an etalon, these together form a thin film structure, and this gives rise to those rings, the colorful rings that we are seeing here, and these are known as Newton's rings, and the figure is from the Wikipedia. So essentially, it's not this coloration that we are seeing here is not caused by the top surface that we definitely see is curved, but it's rather the bottom surface of the lens that should be flat, but in practice it's not. It's slightly curved, and then that has been index matched with an etalon, or just matched with the etalon put on top of a flat piece of a glass. And then we again are seeing thin film structure in place, giving rise to these Newton's rings. And in fact, these rings tell us quite a bit about the surface flatness of my component. So if you would really want to, for example, quantify how flat is some optical component of your interest, you could do these kind of things in a more sophisticated manner, and you could record these kind of interference patterns, and you would in fact be able to calculate by just calculating at the minima and maxima of these interference patterns of the order of change in the surface flatness as a function of wavelength. So essentially you would be able to get kind of estimate how much of a deviation you have in the flatness from the ideal case by just calculating the fringes. And indeed, these kind of techniques are actually being used to quantify optical instruments and their flatness. So I think pretty cool stuff that you can do with these thin film structures and interference effects. And here I'm at the end of this lecture. I hope you enjoyed, especially the final examples. And my apologies if you are a tea drinker. No offense meant towards you. The same effects do also happen there, and in fact, even better than with the coffee mugs. So I thank you for your time and your patience of continually choosing to listen my lectures. I wish you had a good morning, good day, good evening, or good night. And please join me shortly when we are going into the next lecture regarding Michelson interferometers. So thanks and bye-bye.